time evolution of a free particle wave packet. So suppose you know psi of x and 0. Suppose you know psi of x and 0. So what do you do next if you want to calculate psi of x and t? Well, the first step, step 1, is calculate phi of k. So you have phi of k is equal to 1 over square root of 2 pi integral dx psi of x 0 e to the minus I kx. So you must do this integral. Step 2. Step 2. With this, now rewrite and say that psi of x0 is 1 over square root of 2 pi dk e to the, phi of k e to the I kx. So that has achieved a rewriting of psi of x and 0, which was an arbitrary function, as a superposition of plane waves. Step 3 is the most fun step of all. Step 3, you look at this and then you say, well, I know now what psi of x and t is. Evolving this is as easy as doing nothing. What I must do here is 1 over square root of 2 pi, just copy this dk, phi of k e to the I kx, and I put here minus omega of k t. And I remind you that h bar omega of k is the energy, and it's equal to h squared k squared over 2m. This is our free particle. And I claim that just by writing this, I've solved the Schrödinger equation and I've time-evolved everything. The answer is there. I didn't have to solve the differential equation, or that's it. That's the answer. Claim this is the answer. And the reason is important. If you come equipped with a Schrödinger equation, what should you check? That I h bar d psi dt is equal to h psi, which is minus h squared over 2m d second dx squared psi. Well, you can act with ih ddt and on this thing, and you remember all that happens is that it all concentrates on this thing. And it solves this because it's a plane wave. So this thing, this psi of x and t, solves the Schrödinger equation. It's a superposition of plane waves, each of which solves the free Schrödinger equation. So we also mentioned that since the Schrödinger equation is first order in time, if you know the wave function at one time and you solve it, you get the wave function at any time. So here is a solution that is a solution of the Schrödinger equations. But at time equals 0, this is 0, and it reduces to psi of x and 0. So it has the right condition. Not only solves the Schrödinger equation, but it reduces to the right thing. So it is the answer. And we could say that there's a step 4, which is step 4 would be do the k integral. And sometimes it's possible. You see, in here, once you have this phi of k, maybe you can just look at it and say, oh yeah, I can do this k integral and get psi of x and 0, recover what I know. I know how to do. This integral is a little harder because k appears a little more complicated. But it has the whole answer to the problem. I think one should definitely focus on this and appreciate that with 0 effort and Fourier's theorem, you're managing to solve the propagation of any initial wave function for all times. So there will be an exercise in the homework which is called evolving the free Gaussian. So you take a psi a of x and time equals 0 to be e to the minus x squared over 4a squared over 2 pi to the 1/4, that's for normalization, square root of a. And so what is this? This is a psi that is a Gaussian, and the uncertainty is roughly a, is that right? Delta x is about a, because that controls the width of the Gaussian. And now you have a Gaussian that you have to evolve. And what's going to happen with it? This Gaussian, as written, doesn't represent a moving Gaussian. To be a moving Gaussian, you would like to see maybe things of the form e to the I px that represent waves with momentum. So I don't see anything like that in this wave function. So this must be a Gaussian that is just sitting here. And what is it going to do in time? Well, it's presumably going to spread out. So the width is going to change in time. There's going to be a time in which the shape changes. Will it be similar to what you have here? Yes. The time will be related. So time for changes, so there will be some relevant time in this problem for which the width starts to change, and it will be related to m a squared over h bar. In fact, you will find that with a 2, the formulas look very, very neat. And that's the relevant time for deformation of the Gaussian. So you will do those 4 steps. They're all doable for Gaussians. And you'll find the Fourier transform, which is another Gaussian. Then you will put the right things and then try to do the integral back. The answer is a bit messy for psi, but not messy for psi squared, which is what we typically ask you to find.